Let's take a look at how star birth fits onto the HR diagram. If we compare our protostar to the star that it becomes, protostars, remember, are low temperature. They haven't started nuclear fusion yet, so they're low temperature, whereas the actual star is a higher temperature once it ignites its nuclear fuel. But they differ in size. The protostar, because it's still contracting, is much, much larger than the star once it ignites. And so, in fact, a protostar, even though it's a much lower temperature, will actually be more luminous than a star. It will give off more energy. Now, it won't look very bright to us because most of that energy at lower temperatures will be long wavelength infrared radiation. But if we measure that energy as well, then they're actually much more luminous than the protostar. Than the star. So if we wanted to look at where a protostar would fit onto the HR diagram, and we don't fit them onto the HR diagram because they're not stars, but if we wanted to put them on in terms of luminosity, they're high luminosity, which would mean they'd be up here somewhere, but they're low temperature, which would put them to the right of the HR diagram. So they'd be about here. So let's talk about the sun contracting. It's got about 1 solar mass. When it contracts, however, it turns into a star. Two things happen to it. One is, because it's shrinking, it's going to become less luminous. And that means it's going to move downwards on the HR diagram. But also, because it's contracting and heating up and starting its nuclear fusion, it's going to get hotter, and so it's actually going to move towards the left. And what happened with our sun as it went from protostar to star is that it moved down and to the left on the HR diagram and actually took its place on the main sequence right at the level of the G2 stars. So it moved on to the main sequence, starting its life as a nuclear fusing star in hydrostatic equilibrium. And so we actually name stars that have just moved onto the main sequence as ZAMs. ZAMs stands for a zero-age main sequence star. And we can see these stars that have just moved onto the main sequence that are now fusing hydrogen to helium in their core and that are in hydrostatic equilibrium. If you remember, when we looked at pictures showing the formation of stars and solar systems, this is the Eagle Nebula. We're going to zoom in here on what are called the pillars of creation. And if we zoom in even further, we see these strange structures, and what we see is the gas and dust of newly born stars being blown away by the stellar winds that are coming off these new stars. If you remember those clouds of dust that had given birth to a star and were now being blown away, we called them eggs. Those were evaporating gaseous globules. Astronomers love abbreviations. And if we zoom in on one of them, we can see this whole egg here, and that egg contains 3 ZAMs, zero-age main sequence stars. In our next video, we're going to talk about the lifetime of stars. How long does a star last burning hydrogen on the main sequence?